I'd like to introduce our keynote speaker, Wayne Jobert. Wayne Jobert is a computational scientist at the Oak Ridge Leadership Computing Facility at Oak Ridge National Laboratory. He also serves as the Scientific Library Readiness Task Lead for the Computing Facility Summit Supercomputer. Wayne also specializes in developing mathematical methods, algorithms, and software to help researchers solve science problems more quickly and effectively on advanced systems. He is the primary author of the Gordon Bell Prize-winning comparative genomics code called CoMet, the first science application to achieve exascale performance. And Dr. Jobert has earned his PhD in mathematics at the University of Texas at Austin. So please welcome Dr. Jobert to the stage.
Hi, thanks for the invitation to speak today. I want to talk a little bit about a recent work on comparative genomics, but before this I would like to talk about some developments we're seeing in the world of computing I think are very interesting and impactful for us. Basically, we're entering into a new time that's very interesting, I think, time of heterogeneity of computing and processors. Basically, a time in which we're seeing a greater variety of different kinds of processors that are being deployed, as well as on the specific processors, different kinds of features that are being added that make things very interesting. We're seeing this in the general computing market, basically in servers. We're seeing in server farms and data centers. We're seeing, instead of just a standard x86 architecture, which we've seen for a long time, we're seeing new kinds of architectures. For example, seeing FPGAs deployed and things like that, and tensor processing units, which have been developed by Google, and also GPUs of different kinds in data centers that are available. So this trend is also seen at the other end of computing, not at the small scale, in mobile devices. John Schauf at NERSC has pointed out that the iPhone actually has on the device 30 different kinds of accelerators for different operations, such as decoding audio and playing video and this sort of thing. So increasing diversity of processors and features, and this was spoken to previously by Herb Sutter, who described it as a compute jungle, that we'd be seeing more and more of this, and it would be a challenge to us as software developers to keep up with this. These trends are also seen in the HPC market. Back, if you look 7 years ago, there were only a handful of systems that actually use GPUs, for example, Keeneland or Titan systems. And today, for the first time, we've seen in the top 500 list last year, we saw a tipping point in which over half of the floating point operations on the top 500 list are now being delivered by GPUs. We're seeing compute nodes on these systems are becoming more complex. As you can see in these two diagrams, Titan had a single GPU per compute node, and if you just look at the bottom picture, Summit, it's just visually much more complex. We have 6 GPUs per node. We have complex NUMA domains, complex memory situation, sort of two halves of the node that are semi-isolated, and also SSD device that is on the node. So we're clearly getting more complexity, and also on the specific GPUs we're seeing new features. For example, reduced precision features on the GPUs. And these changes are happening for mainly because we're seeing sort of a slowdown in the trend we've seen for decades of exponential increase in computing power in processors. We're seeing that power is a limitation, and also seeing the struggle to reduce the feature size on the silicon. And in order to continue progress, vendors are resorting to other means, like different kinds of architectures. This is bad news for us because we're the developers who are facing running our science on these kinds of devices. We have a challenge of portability, performance portability, as different vendors are coming up with different kinds of GPUs, devices with some differences in the memory hierarchy. And we usually, most of our users want to run their codes on multiple centers, and so keeping up with this is hard in terms of code maintenance, and also it threatens in the longer term the ability to continue to deliver increases in performance. We're not sure, as described in the talk yesterday, we're not really sure exactly what's going to happen with quantum computing. We're hoping that it's actually fruitful, but there's uncertainty moving forward. But there's also some good news here that some people have described this as a golden age of processor architecture, computer architecture, opportunities for new innovations, and also there are exciting opportunities for us as well, I think, in terms of new opportunities to use this new hardware, maybe in a way that has not been thought of before, that could greatly accelerate our output of science. I wanted to give just a little bit of the background of how we got here. Heterogeneous computing is not really new. We saw it in the 70s and 80s with the old pipeline vector systems. The Krell vector systems had pipeline vector units, but also scalar processing units. And so it's really not new. However, this sort of came to an end in the early 90s with what's been called this supercomputing market crash, where basically the dominant paradigm became clusters of commodity processors programmed with MPI. And this was the kind of the dominating paradigm for about 2 decades. But at the same time, there were concerns that are arising that this would not be enough to get us to exascale, and perhaps not even be very effective at petascale either. And one particular effort was the Los Alamos Dark Horse project, which had these concerns, basically saw that most of the budget of silicon on the chip and the power budget for our processors was not dedicated to floating point operations, and also there was a growing distance between the floating point rate of these processors and the near memory. For example, there are some processors in, say, the early mid-2000s that for which the flops per byte versus the bandwidth of reading from memory might have been a factor of 100, reading the flop rate for a single processor core versus the memory bandwidth. This growing disparity, and so this work was actually prescient. They looked at GPUs even at this early time, FPGAs, and also they looked at what is today become standard for GPUs, high bandwidth memory. Now, the next question would be, can you actually run codes of interest to the DOE on these kinds of processors? And so there was a research project at Los Alamos that was fairly well funded and looked at a range of DOE applications to see, could these actually be ported to these kinds of architectures? And this was followed by the Lanel Roadrunner system. It was the first system to hit a petaflop. It was an ambitious system. It was not a perfect system by any means. One issue with Roadrunner is that there were actually 3 kinds of processors you would have to write code for. There were the CPU, the GPU, and on the GPU there were vector units, and you had to write 3 separate kinds of code for those 3 units. And in particular for Fortran developers, it was a real challenge. And in spite, though, of its imperfections, it did actually succeed in its mission, which was, first of all, to show that it was actually possible to solve science problems on heterogeneous kinds of GPU-accelerated nodes. But also, it served its mission in terms of delivering science during its tenure for the ASC program. Moving forward to 2008, around this time, a little later, the famous Peter Kogi report on exascale, and made many predictions, talked about the challenges of getting to exascale. And one thing in particular it mentioned was that they predicted that it would require up to half of a gigawatt to basically power an exaflop system. which would require basically about $500 million a year just to pay the power bill for a single system. Some people quip that maybe we need to build a single nuclear reactor that would have single purpose of actually running one of these systems. But an actual number that's coming out that's expected for the systems in the next couple of years, the exaflop systems, actually about a factor of 10 less than this, and partly this is due to GPUs. Also around this time, in April 2009, Oak Ridge began discussions with Krell about their next system, which would turn out to be GPU-enabled and would be eventually named Titan. There were many early discussions we had in the early days about what applications could we run on this system, what could we do, was it actually feasible to do, how were we going to move forward. And it was deployed in June of 2013, and it's actually going to be decommissioned on August 1st, very, very soon. Actually was quite a bit easier to program than Roadrunner. We had CUDA, and in this time period around 2011, OpenACC came online, and one of the early readiness apps, S3D combustion app, was actually implemented in OpenACC. Since then, we've had other options come out. OpenMP has adopted the offload directive, and also middleware such as Cocos and Raja have made it easier to program these devices. And over its tenure, Titan has delivered billions of compute hours to numerous projects for moving science forward. And now all of the announced systems in the DOE complex will be accelerated, whether it's El Capitan, A21, Frontier, or Perlmutter, they'll all be accelerated. So there's been a sea change in that, but yet at the same time that we've all come to accelerated computing, we're seeing still new developments. In particular, I'm referring to reduced precision hardware, specifically the tensor cores that we're seeing on the NVIDIA Volta GPUs. And so I wanted to talk a little bit about that. The tensor cores are a new development. They were announced at NVIDIA GTC in 2017. They're basically hardware on the GPU to accelerate reduced precision computations. The motivation for these was the growing data workloads serving the needs of deep learning, as it was discovered that reduced precision was adequate for this. Basically, you can perform a matrix-matrix product in half precision at 16 times faster than double precision. And so great opportunity for acceleration for apps that can use that operation. And NVIDIA is not the only vendor. The Intel Knights Mill processor, which is no longer in production, supported higher reduced precision rate. Also other processors, Google TPU, the AMD Radeon is supporting reduced precision. And also by one reckoning, there are about 50 startup companies that are trying to develop custom processors for deep learning with reduced precision, in some cases as low as single bit. And obviously, this is another step in heterogeneous variety of processor hardware. And this is not escape notice of app developers. Last November, 4 out of the 6 Gordon Bell finalists actually used the tensor cores for their work. And in particular, I'd like to talk about one of these applications, the CoMet application. CoMet is a new application. It's for comparative genomics. Its purpose is to find patterns in genomic data, in particular interacting genetic elements in a genome that are causing certain traits, for example, Alzheimer's or susceptibility to opioid addiction. It's not a traditional HPC app. Traditionally, in the past, the main bread and butter has often been PDE solvers. It's not a PDE solver. It's not a particle and cell code. It's not a fusion code for solving using particle and cell methods. It's not a Monte Carlo code. It's also not an AI code per se, deep learning code per se, though it is used by the team in an AI workflow. It's, I think, best described as a data analytics application, which I'll describe in the coming slides here. Basically, its purpose, as I said, is to find patterns in the genomic data, patterns of interacting genetic features that cause certain traits, for example, susceptibility to a disease. Unfortunately, it's not known a priori what these features are in the genome and which ones are actually interacting to cause these traits. And so this leads to basically a combinatorial explosion, options basically to compare all these to each other and figure out which ones are causing these features. Mathematically, this reduces to a vector similarity search problem, all-to-all comparison, and this has a known computational complexity, order n to the km, where k is the size of a cluster of interacting vectors. The vectors represent the features. M here is the number of vectors, and n is the length, which would be the population size. So it's high computational complexity, but it's also challenging because being an all-to-all computation, it requires communication, very heavy communication. It's not like a PDE solver, which has a local interaction and kind of halo communication and low communication needs. It's actually very communication intensive as well as computationally intensive. So how is this problem to be solved? It's a vector similarity search problem, but it's actually known that this is kind of a solved problem already, that it has a same computational pattern as a known problem, which is dense matrix product, which has been studied for decades. The GEM, or general dense matrix product. This has been studied, it's been optimized, and in fact it's actually implemented in well-known libraries such as ELIPAC, cuBLAS, and MKL. So these libraries have been optimized to the memory hierarchy, and so a lot of the work has already been done in solving problems like this and can be exploited either directly or by modification of these libraries. And I didn't want to get too detailed here with the formulas, but I'm just going to put up here some of the methods that are used. Mainly, we're interested in something called a custom correlation coefficient. And the main aspect of this is that it will take pairs of vectors and compare these vectors element-wise, and after creating a bit which represents the relationship of those entries, summing up those bits. Those vector entries actually can be stored as 2-bit values. They're used to encode the allele data that's in the genome. So it's actually not a floating point operation at all, but it's a bitwise operation. And next slide is how this is implemented. So this is shown diagrammatically on the bottom of the slide here. We have these long vectors which have 2-bit entries. The different combinations of bits in these vectors are enumerated, and the number of occurrences of these patterns is tallied into a table. And this kind of summarizes the algorithm. So how this was implemented in the first version was to exploit the Magma library, which already has the code to manage the memory hierarchy for this kind of operation, and modifying it to use bitwise operations to implement this method. And in particular, there's a population count intrinsic on the GPU, maps to hardware. It's able to sum up the bits in a 64-bit word very rapidly, so we can exploit hardware operations on the GPU to do this. But subsequent to this, we developed a new method which uses the tensor cores and actually standard GEM operations. We found out it's possible to rearrange the matrix by sort of a mathematical trick and use half precision hardware. In fact, we could actually do this even if we had 2 bits of precision for the input, and accumulate these to FP32, 32-bit values, and actually run this very fast on the tensor cores. And since their tensor cores are 16 times faster than 64-bit arithmetic for similar operation, we can actually use this to advantage. And I want to skip some of the details of the algorithm and go right to the results here. Here are some scaling plots on CoMet for CoMet code. Basically keeping the work constant per GPU and scaling out to nearly the whole system. There are lots of different methods. We have methods to compare 2 vectors at a time or 3 vectors at a time and different variations. And the upshot is they really all scale very, very well. And this is actually made possible by the CoMet hardware. Unlike Titan, which had a 3D torus for which we actually saw congestion, we actually have a very good InfiniBand fat tree network, which is nearly congestion-free because of adaptive routing. Basically, for this, we have messages. Every GPU is sending a message of nearly a gigabyte in size to another GPU, so there's a lot of communication happening at the same time, and there's a big risk of congestion. But we have very good hardware for handling this, so we're very happy with this feature of the system. And this is just a slide for the maximum achieved performance at 99% of the system. And there are lots of methods that were tested, but in particular the CCC method, two-way CCC method, which we're most interested in. We achieved 2.36 exaops performance. It's the first exaop calculation by an application. And also we're getting about 75% of the peak speed of CoMet, the peak mixed precision speed achievable by CoMet. So we're actually achieving sort of an exascale class performance now on a pre-exascale system. We're about 53 times faster than running this on Titan. But of course it should be pointed out this is mixed precision, and we're not going to see real true double precision, which is needed by the majority of the apps until we get true exascale systems in around the 2021 timeframe. So also a comparison to state-of-the-art. Basically, since these methods are relatively new, because we haven't had great amounts of genomic data for a long period of time. We've been solving PDEs since the 30s and 40s, but this is relatively new. So these methods are relatively new. And it's actually, there have not been a lot of efforts to port these to GPUs. There have been a few efforts to port to GPUs, not many, and very few attempts to port to HPC systems. They're in the literature, so basically look for all the comparative work in the literature. The fastest known method, basically a two-way method, was implemented on Edison system, which is decommissioned in last May. And basically CoMet runs about 20,000 times faster in terms of its science output per second compared to that. And in terms of three-way methods that compare three vectors at a time to find three-way interactions, there's been less work in the literature. In particular, there was one paper that had worked on four NVIDIA GPUs, and CoMet is 300,000 times faster than this. And the basic reason for these great speed ups over state-of-the-art is simply that essentially these efforts have never really attempted to use systems with very large number of GPUs. And also want to give a result on a real-world problem. This is a human genome data set with about 80 million vectors, length 600,000. This is a publicly available data set. And basically, this is run on 2/3 of CoMet. This is an entire run time shown here. This is complete with overheads, including I/O. We're using for output, we're using the burst buffers on the node for very fast output. And basically, as you can see here, only 11% of the time is spent in I/O and other overheads. We're getting 89% of time spent in the core algorithm. And run on 2/3 of CoMet. This runs at 1.5 exaops performance, and very consistent with 2.36 exaops on the full system. And this job was run in 3 hours on CoMet, and if run at the speed of the comparable state-of-the-art, it would take 15 years of wall clock time to run. So we're very pleased that this is going to enable us to run new problems that we haven't thought about before. And I want to just thank the team for this effort, for first application, and also the Gordon Bell Award, and thank the team for the team effort on this. But also wanted to point out, as I mentioned before, we're not the only ones looking at reduced precision to accelerate applications. There have been, as I mentioned, there were multiple Gordon Bell entries in 2018. I'm aware of at least several, and 2019 applicants to Gordon Bell are using reduced precision on these systems. At SC18, there were about 15 different presentations and posters and sessions discussing how could we use reduced precision in a variety of areas. One interesting tool was, one of the posters was a tool you could actually run on your code that would try to identify the parts of the code that could be run in reduced precision. So there's a lot of interest. And this slide here I got from Stan Tomov at the ICL shows a speed up they're achieving for solving dense linear systems. They're getting like a 4x speed up by using iterative refinement. The result they're getting for their solving these linear systems is full double precision, but they can actually use the half precision units on the GPUs to accelerate this, so there's no loss of performance for the final result. And we're also at Oak Ridge, we're looking for other opportunities. We're having discussions with NVIDIA, with our colleagues at Livermore, at ways that we can actually find more opportunities to accelerate applications. It seems that we're not at the end. I think some of us were hoping that we're at the end. We've converged to sort of a common architecture of GPUs, but as soon as that is happening, we're seeing other features introduced. But we're not seeing an unmanageable amount of heterogeneity yet, at least. But we are seeing different new features coming up. And there have been various predictions that have been made. I just want to call some of these and repeat some of these that are kind of interesting. David Patterson, the computer architecture luminary, said at a scale meeting last year that what he sees coming is basically domain-specific architectures, not just domain-specific languages, but domain-specific architectures customized to the specific application areas. Just a couple of weeks ago, Jack D'Angara had a talk entitled, by 2030, there will be no more general-purpose computing, that we may end up with the different science domains having specific architectures that we need to port to. Also, for some time, Lucy Knoll at DOE has been tracking different kinds of accelerators that are coming along. There was a heterogeneity workshop in 2018 that listed some of these, talking about possibly eventually neuromorphic or quantum accelerators on our next supercomputers coming up in the future. Also makes for interesting reading the IEEE roadmap beyond CMOS, which predicts certain types of technology which might eventually pan out, such as analog computing, probabilistic circuits, and reversible computing. And in fact, some of the vendors are actually starting to look at this. Bill Daly, the CTO at NVIDIA, has mentioned they're looking at and just experimenting with analog computing. So actually some of these are already getting attention in some quarters. Just as a sidebar, in terms of our need to program these devices, I think we've all been saying for a long time we'd really like to just express our science, express our mathematical algorithms in some easy, neat way in Python or MATLAB, and not worry about the underlying architecture. We just like it to run fast and give good results, and not worry about having to porting to the part of these architecture, not have to worry about that at all. And there have been, for several decades now, there have been various attempts to do this, various claims have been made, different kinds of languages or tools that have been developed to try to make the parallel or accelerated aspect of this sort of invisible to the users. many claims, but there's really been no silver bullet. There's been no automatic parallelizing compiler that's been universally successful in spite of the claims. And though there has been certainly some help and some useful developments, we now have directives that we can use to decorate codes to implement parallelism or acceleration. This can be helpful. Also abstraction layers, libraries such as Cocos and Raja, which can somewhat extract away from the architecture and make things more portable and easy to program. And also domain-specific languages in situations where it makes sense can be helpful. It is obviously understandable if we didn't have to port to GPUs or these new heterogeneous features that are coming down the line. Just like 20 years ago, people were saying, I really don't want to port my code to MPI. And that's okay for many science applications. People are doing good science at a small scale. It is very important. However, at the high scale, what we've seen is that there are some codes that have been unable or just have not adopted GPUs, and essentially they've fallen out of use for leadership computing. And specifically, there's one code that was used in inside projects at the DOE for some time, and it's simply been replaced by another code which could use GPUs. So I think it's important for us just to realize we have to be using these systems. For CoMet, over 95% of the flops and the memory bandwidth are provided by the GPUs. So unfortunately, it's just a way that things are going and we need to adapt to. I want to just have a comment here about what I feel is a critical role of algorithms here. A lot of the really fundamental breakthroughs in computational science in recent decades have come from new algorithms which drastically change the computational complexity of computations. For example, the FFT, which reduced the Fourier transform from order n squared to an order n log n operation. Also, multigrid, which for suitable problems reduces computational complexity from superlinear to linear in the number of unknowns. And these have made major breakthroughs for different science domains. Also, sometimes more important than parallel computing. And one thing that comes to mind is mixed integer programming codes, which are used for solving scheduling problems in industry. They've achieved about factor of a 500,000 speed up over the last 25 years due to increases in hardware performance. However, a 1.5 million factor speed up from advances in algorithms, new heuristics, and advances in software. So algorithm development can be very important, and particularly in finding new ways to map difficult algorithms to hardware. This can be very important and lead to breakthrough results, and a few examples of this come to mind. For example, ray tracing algorithms, which are used for CGI and rendering, which had been thought for some time not to be possible to map these to GPUs, and they in fact have been. Also in Monte Carlo radiation transport, the nature of these that they have not mapped very well to vector units are GPU warps, and there are new methods, the event-based methods, which are successful in mapping these more efficiently to GPUs. Another example would be an algebraic multigrid. 3D problems originally could not be solved in parallel very efficiently due to communication, but there's been the application of aggressive coarsening methods to increase the sparsity of the coarse grid matrices has made this tractable problem for large parallel systems. Also an effort in ECP, the Seed Co-Design Center, to essentially convert what were thought to be sparse problems which could not be mapped efficiently to hardware are now being solved at high computational intensity due to a higher tensor elements. Also, communication avoiding Krylov solver methods, which deal more effectively with communication for these linear solvers. Also, as I mentioned, reduced precision, dense and sparse linear solvers, and also for radiation transport. Also KBA methods, which were implemented to improve performance, map these to parallel hardware, and also been applied to accelerated processors. So I wanted to, I'm a little early here getting through the slides here, but I just want to move toward the end here. Just kind of some thought problems, example challenge problems here, just some ideas to throw out in terms of what sort of things we might be facing in the future. For example, how could you accelerate your science algorithm on a processor that doesn't have a floating point unit and perhaps doesn't even have an instruction set? And I'm thinking about the neuromorphic processors, which are basically inspired by brain structure. They basically are designed to implement spiking neural networks, but they have actually been used to implement simple diffusion solvers. So people are actually trying to take these devices, which are meant for machine learning and deep learning, and are mapping these to science problems. Is there a way to map this to other kinds of science problems that might be interesting? And why that might be important is that they run at orders of magnitude less power than conventional devices. Another thought question, referring back to quantum computing, if there was an operation that would run order n time instead of order n squared time on a conventional processor, is there some way that we could use this for applications? So actually, there are some algorithms like this. Can we use this for the science that matters to us? Another example is, what if we could run a matrix-matrix product 100 times faster than a conventional way by representing the inputs as 1-bit values? In fact, this is available today on the NVIDIA Turing architecture, where potentially this can actually be done now if your application can actually make use of this with just 1-bit inputs. And also, what if you had a very fast analog computing circuit that would give you an initial guess to your problem which you could refine by conventional means? Could this be used to advantage? And finally, I wanted to just give a reverse kind of a question. Instead of starting with the hardware, can we start with our algorithms, the different motifs within our algorithms, the computational kernels? Can we take these across different applications and abstract these into idealized kernels that we could go back to the vendors and say, hey, it would be really useful if you put this in silicon for us. Is this at all possible? And we're not sure if they would, but I think it's an interesting thing to think about. So just conclusions. I think we're entering into a challenging time now. We still can manage the amount of heterogeneity we have. We have some amount of convergence with sort of a common architecture now in having GPUs, but it looks like increasingly we're going to be seeing new kinds of features that are coming online. This will be challenging to us as application developers and maintainers, but also exciting time as there'll be new opportunities to exploit this kind of hardware. This may come out unexpectedly. 2 years ago, tensor-cores came out, which were sort of not even on the radar screen 10 years earlier. It came out all of a sudden, and so they provide new opportunities. Some applications will not survive the changes that are coming forward. Some will adapt, some will be rewritten, some will be some new codes will be written, and CoMet is one example of an application that was able to take advantage of new features, new hardware features, and have a great advantage from doing that. We will have a performance portability problem going forward, maintaining these codes, different kinds of features for different platforms, maintaining this in a single code base will be a challenge. And I think that regarding algorithms, we'll need to be aware of the current art, the prior art, the current state-of-the-art in algorithms, but be ready to take sort of a totally blank sheet of paper approach to some of our science problems, perhaps totally different kinds of approaches to solving these problems with new kinds of hardware. And we will need diverse kinds of skills, approaches, problem-solving methods to be successful at this as team effort will be very, very important going forward. So that's pretty much all I had to say, and I'll take any questions.